Hello everyone, it's Robo Theory, and this is my 10th video, concept number 9, because my other video was a short introduction. And basically in this video we'll be talking about robot languages, so we'll be going more in depth. So what I have here is the successfulness of the robot. So the successfulness of the robot is based off the responding behavior to the environment. So how the robot responds to the environment based off of how you programmed it to. For example, how you program the robot. So for example, programming the robot to execute the task, as this guy is doing, then testing the robot over and over while changing the program to maximize effectiveness. So basically in these two steps, number one, you're going through the program and typing it in. You have to type in all the code, maybe all the comments, and you have to make the final code of what your robot wants to do. For example, if it needs to move forward, then you set the motors to go forward, like rotate a certain amount of time. Then you open the claw, and you go a little more forward, close the claw, and then you lift up your arm. Let's just say that might be your task. And then you test that. Maybe rarely on the first time it works. However, as you start to progress, you test the robot and you analyze what happened. For example, we see over here that this bar might be high. I'm just taking this off the picture. This bar might be high. This might be how the robot was effective based off of the speed. So maybe the robot was going at the right speed at the right time. And maybe this data point over here was talking about how it opened its arm. And maybe this data point, this is all the way down here, was maybe referring to the robot might have accidentally broken its arm somehow. Maybe because it might have closed it too much when closing. So these data points have to be analyzed and then programming the robot. So you have to repeat these tasks over and over. So now let's talk about the language generations. So this is mainly about the slides. So basically computers mainly understand binary code, which is zeros and ones. So this is known as first generation code. The higher the generation of the language, the easier it is to program and the closer it gets to human languages, natural languages, as some call it. So we only go to the fifth generation language because it's more of AI techniques. This is stuff that our generations are still learning, whereas the sixth generation is something that still hasn't been tapped into. It still needs to be discovered almost. So using more generations requires high-tech computers and is hard to implement. So you can't just start talking like move the robot forward. That can't be your only thing in your program, because it will be like a 10th generation program, or maybe an 8th generation. So typing in move robot forward, it's very generic. Might even sound it's like a basic pseudocode, which is regular natural language writing of the code. So these are, as the generations go on, the microcontroller has to be more compatible with these specific things. So what we typically programming in is second to fourth generation. Second generation language is Fortran and COBOL, COBOL. Third generation is the most common, which is Java, C++, Python, anything like that. And then fourth generation is SQL. So now we're going to look at how these languages might seem easier. So to start off with, the first generation languages look like zeros, ones. Really hard to understand. However, if we were to program using first generation language, it might fail most of the time because you might have missed a 1 or a 0 here, maybe added 1 too many ones, 1 too many zeros here. So it's really a shifty language to learn. So then second generation languages were made, and now we can see that we have some things that we can understand out of this kind of algorithm. Then we go to third generation languages, we can understand a few words here, and we can kind of see what's happening, but some things are still a little concerned and confused about. Then we go to fourth generation languages, we can see that this is all words that we can mainly understand. almost all of them are words we can understand, and it might be easy to program using this. And then fifth generation, these are all words that if you do speak English, you would know. So these are all words you would understand in fifth generation, and sixth generation would be a lot more easier to understand based off this. And no, this is not the same program. I got these off of Google Images. So examples of third generation languages, I'm just going to give three of them. So Java, Python, C++, and as you can see, they are different. However, they do have the same goal. So if you want to calculate the area of a circle based off of a given radius, for example, not the, yeah, radius of the circle, you want to calculate the circumference area based off the radius of the circle. So you would write in the formula, maybe in Java you would set some different things. So Java and C++ are mainly dedicated to more of job works, whereas Python is mainly dedicated towards kind of gaming and kind of drawing too. So, but that's not always the case. So now let's go on to one main topic, graphical programming. So graphical programming is fifth generation and it's basically blocks programming. So blocks programming was designed by a university and it consists of drag and drop blocks. Behind the scenes, it is actually translating to low-level languages. I put high-level languages as referring to this chart, saying this one's is higher. The first generation languages are higher. I was referring to that. But if you think of it mathematically, no, numerically, they are low level languages. So for example, in FTC there's blocks programming and it has a Java interface behind it which can also be programmed in. So you might be thinking, why can't you just use blocks for sending a man to the moon, for example, sending a rocket up? Well, mainly because blocks seem like a higher level of abstraction, and the main reason it was created by a university was because they wanted kids to learn how to do blocks programming. They weren't trying to focus it mainly on higher level goals, and using a high level of abstraction like blocks programming, it'll make the programmer not focus on how to solve the problem, but more on what to do to solve the problem. So it does have limitations though on how specific you can be while programming. For example, in blocks programming, you can send a rocket to the moon, for example. So if thrust is 1500, so you can calculate how a plane will move, for example. But if you want to change and test things out, then you obviously need to use a third generation language. Third generation, second generation, and first generation languages are languages that are more specific you can get into, especially first generation, but even though it is binary, it is hard to understand. So now let's talk about one of the main things in the microcontroller, which, as I was talking about in the previous video, is the processor, which translate input code, aka program, into binary code, which only the computer can understand. So, but inside the processor, there's even more. To simplify things, there are four main components to the translator. Translator, processor, I'm just mix and matching these terms. So first of all is the code instruction, which is developing the code for which the robot must follow. So you must type in the code. First, you should have the pseudocode, which is to move the robot forward. Next, you should make it a little more specific as to move the robot forward 10 meters. Open claw, move robot forward 1 more meter. Close claw, lift up arm, and then specific speeds. And then you start to get to where you can start typing in the program, setting in comments so you understand what is happening at that time. Then you can start compiling, which is mainly what the computer does, and it interprets each moment and signal of the code and translating into binary. So compiling and interpreting should not be mix and match terms. So do not say, oh, we're compiling this algorithm, we're interpreting this algorithm. Compiling is when the program gets compiled, it gets sent through binary code, understood, and then it gets executed. Whereas interpreting is more where it just goes through both of them at the same time. So as the code is running, it's also getting executed. So there are pros and cons of both. However, let's continue talking about the processor. So number 3 is assembling. So you're basically combining the configuration and the code. So you're combining, configuration refers to where motors and ports are. So if port 1 has a specific ARM motor, then you have to configure into your code that port 1 has the ARM motor. That way you can program and finish up any doubts programming. And then you execute by applying the code to the output ports. So this isn't referring to the processor in general, but this is mainly referring to the steps as to how the processor is used throughout this whole section. So thank you for watching. Remember to follow me on Instagram and to subscribe and like. If you have any questions, please let them in the comments. Thanks.